Hey everyone, this is Miss Reese. I am going to go over the toolkit page 16 with you. So feel free to fast forward to any portion or part of this toolkit that you need filled in. Okay, so first we're going to be practicing finding areas of regular polygons using the side angle side method and then using some trig ratios. Okay, so first question, we have an 18 gone. Well, that's going to be a little difficult to draw. So we are just going to imagine or draw the triangle that comes within that polygon. So I'm going to give you a little demonstration here. So kind of looking like this, it would be like one of the full triangles is what we're going to focus on here. Okay, so it's going to be a pretty tall triangle here. And the radius of the triangle is 20, and that's from the center of the figure to the vertex. So I'm going to put 20s on both of these pieces here. And then in order to find this angle here, remember that's our central angle, we would take 360 and we would divide it by 18 because there's 18 sides to this figure. Okay, so that's going to give us 20 degrees. This happens to just be a coincidence that the radiuses of this figure are 20 and the angle measure is 20. So now if we're setting up to find the area for just this one triangle would be 20 multiplied with 20, multiplied with the sine of the angle that's between them, all divided by 2. That's the side angle side method. Now, what we also need to take into consideration is that this is an 18 gon. It's an 18-sided figure. So it will have 18 of these triangles. So this would be how we would find the area. We can just put this all into our calculator. So try getting yours out and we can make sure that you are getting the same value as well. So 20 times 20, you could use parentheses if you want as well. Sine 20 and then times 18. And we're going to divide that all by 2. So our area is approximately 1,231 point, and then I always round to 3 decimal places. So 272 would actually round to 273. We always look at the number after the first 3 numbers to determine if we round the number up. And then our units would be feet squared. Okay, so that's our first figure. In the second figure, we have a pentagon. That one's a little easier to draw. So let's see how close mine can become to a regular pentagon. Let's just pretend. Okay, and we have the apothem length. That's from the center of the figure to the center of one of its sides. And then now I'm going to create a right triangle out of that. And so the apothem is 20, so I'll place the 20 here. And now if we're focusing on this triangle, let me make sure we are looking at the same one. So I'm focused on this highlighted triangle here. I know the height of that triangle, but I don't know the base. So I'm going to label this base, that's just this half length here, as x. So in order to find that, we also need an angle measure. This is a half central angle, so we could take 360, and I would be dividing it by 10. And that's because I can fit 10 of these angles in the center of this figure, 2 per side, and there's 5 sides. That's going to be a 36-degree angle. So here we go. Now from here, we can use a tangent ratio, opposite and adjacent. So we can say tan, remember SOHCAHTOA, TOA, tan of 36 is equal to the opposite side x over the adjacent side 20. So in order to isolate x, all we have to do is multiply both sides by 20. So x equals, or we'll say it's approximately, let's multiply 20 with the tangent of 36. And that's going to be about 14.5. 530 is going to round to 531. Okay, so that's our value for x. Now there's 2 ways to do this. You can either double x so that you get the full side length here to this triangle, or I'm just going to focus on the area of this little half triangle. So I would say the area is approximately, let's say the base of this highlighted triangle is that 14.531. The height is 20 divided by 2. Now we need to just imagine how many of those actual triangles we can fit into this shape. And since I can fit 2 on each side and there's 5 sides, I can fit 10 of them. So multiplying this all out will give us our approximate area. It would actually even be more accurate. Let me leave the 20 times tan 36 in my calculator. Be more accurate actually to have this answer just continuing. So I'm going to multiply that by 20 and by 10 and then divide by 2. So our approximate area is 1,453. 0.85 or just 85 would stay 85. So we'll do 0.85. And that would be feet. Yes, we're in feet squared. Okay. Now, if you use this number, your answer might have been slightly off, but the more you round your answer in the beginning of the answer, the more your answer is off towards the end. Okay. So this is all having to do with the areas of regular polygons. This week, we then focused on and moved into ratios of similarity. So let's look at this to start. So to do this, we can actually draw a little diagram of a square. You can use the actual side lengths if you want, or you can just kind of draw your own little square, and we're going to imagine that we have side lengths of 3, so 3 and 3. And then we're making a new square, and the side lengths are going to be 5s. Let's do here 5 and 5. So what we want to know is what is the ratio of their sides. So for ratios, we're going to say that we're going to use a scale factor. So let's just remind ourselves, what's a scale factor? Scale factor is always the new side length, and we're comparing that to the original side length. So I'm going to say that this is the original figure. This is what we're starting with, and let's just call this the new figure then. Original and new. So our ratio is going to be 5 compared with 3, or 5 over 3, ratio of their sides, 5 to 3. Okay. Now to find the ratio of their perimeters, we're actually going to need to figure out what their perimeters are. So this square has 4 sides. Well, they all have 4 sides. So this would be 3 times 4. The perimeter of this figure is 12. And the perimeter of this figure is 5 times 4, which is 20. So the ratio of our perimeters is going to be 20 over 12. And we should simplify that. We can simplify by 4, divide each of these by 4, and that becomes 5/3 as well. So we're noticing that the ratio of the sides and the ratio of their perimeters are the same. Okay, and that's because they both are represented by something linear. Now let's look at the areas of both of these figures. So the area for this original square is going to be 9, 3 times 3, right? And the area for this new square is going to be 25. So we might initially anticipate that the area ratio would be the same as well, but you probably learned in that last lesson on page 16 of your packet that just because you're doubling the side length of something does not necessarily mean that you're doubling the area, right? So the ratio of the areas is actually 25 compared to 9. And 25/9 is as simplified as it gets, okay? So anytime we have ratios and they're in fraction format, right? So we would have linear ratio. Let's just turn these into two variables. Let's use A and B. So A over B. That means whatever we have for the side length ratio is going to be the same for the perimeter ratio. That's going to be A over B as well. And then for our area ratio, that's going to be A over B, but we're essentially taking 5 and squaring it and 3 and squaring it. So we're squaring our fraction. So we can say A over B squared. Now, you don't always necessarily get a ratio or like a fraction when you're making new figures. So let's just say, for example, I start out with a square and my units are 1 by 1. Okay, and then I'm doubling that kind of like you did with the triangle problem. And let's make these 2 by 2s. So let's compare kind of the side length ratio, the side length ratio. This is the new figure. This is the original figure. Is going to be 2 over 1. So 2 to 1, or let's just say 2, side length ratio. Side ratio equals 2. For the perimeter ratio, well, the perimeter of this first figure is 4. So perimeter ratio. Perimeter of the first one is 4. The perimeter of this new one is 8. So 8 over 4, which is 2. Okay, good. They're the same value. Oops, sorry, you can't see that. And the last thing we want to look at is comparing the area. So the area of this figure is 4. The area of this figure is 1. So our area ratio is actually 4 over 1, or just 4, right? So that means if we don't have it in a fraction form, we can also say R for the ratio, and we put this in a different letter or color. So our ratio could also be R. We'll call it R for ratio, and then we would just take that value and square it. So as we see here, our side length ratio, our perimeter ratio, they were the same, but our area ratio is this number, but a squared version of that.